Hello everyone, I'm Sangramjit Kumar and today I'll be presenting our project titled Practical Low Light Image Denoising from PMN Baseline to a Full RAW RGB Imaging Pipeline. This project focuses not only on improving denoising performance but more importantly on transforming a research model into a practical and usable system. For motivation, let's look at the wolf image. Low light imaging is a challenging real-world problem. When images are captured in low light, sensors amplify signals which also amplifies noise. Dark shading introduces structured distortions. Camera pipelines further distorts colors. As a result, images become noisy, unclear, and lose important details. Traditional denoising methods often fail here because they assume simple noise, whereas real camera noise is complex and structured. So the goal of this entire project was to build a practical denoising system that works on both real raw and RGB images. Here is the entire outline of this presentation with the flow. First, I will explain the problem and the PMN baseline. Second, I will present the extension as implemented. And finally, I will show the results and a live demonstration of the entire project. Why PMN was a strong starting point of our project? Uh, because it approaches denoising completely different. Instead of directly learning noise removal, it first simplifies the data distribution using pre-processing steps. This makes the learning problem easier and improves performance on real raw images. So in our project, we used PMN as the foundation and extended it into a full pipeline. Real noise is structured. What do we mean by that? In the entire denoising process, one key challenge is that real low light noise is not that simple. It includes short noise, which depends on signal intensity, dark shading, which varies spatially, read noise, and ISP distortions. Because of this, simple Gaussian assumptions do not work. This is why low light denoising is much harder than normal image smoothing. Here is a description of the dataset and raw representations of what was used in the project. We use SID and ELD dataset which provides paired low light raw images. Instead of using RGB images, the actual model processes packed paired raw data with 4 channels. This preserves sensor level information and allows better restoration. Here is the paper pipeline, PMN pipeline, which was used by the researchers. During training, noise is simplified, data is augmented, and during inference, the model directly restores raw images. This structure improves performance on real-world data. Moving on to the key two ideas of PMN, SDC and SNA. SDC stands for Dark Shading Correction, which actually removes structured biases, and SNA stands for Short Noise Augmentation, which increases training diversity. Together, these two form the core part of our project and they improve learning and final output quality. The baseline already performs well. Strong raw restoration, better detail prevention, good benchmark performance. But however, this is still not a complete system usable in real world scenario. Where comes our extension of our project? What was missing in the original paper? The original PMN lacked practical features such as direct raw inference, exposure handling, RGB support, low memory execution, low memory execution, GUI, and simple deployment support. So our goal was to bridge this gap. Here are the project deliverables. We implemented a complete system, multiple modules comprising of many modules such as the core inference pipeline, benchmarking tool, GUI application, video denoising, which was completely added by us, synthetic data generation, RGB fine-tuning, model export. So this all work was done by us as an extension of this original research. So this project is not just a model, but a full workflow system. This pipeline flows the raw processing pipeline. We read raw files, normalize them, apply exposure scaling, run model inference, then perform post-processing. This makes the output usable for real applications. One major issue we found was exposure mismatch. The model expects amplified raw inputs. Without scaling, outputs become very dark. We fixed this using ratio control, which significantly improved result, which we will see in live demonstration. Low resource improvements. We added three major improvements. First, tiled inference, which splits large images and reduces GPU memory usage so that this project can be used by everyday computers. Second, auto ratio, which automatically adjusts exposures. This was useful for the RGB images. And for the last part, diagnostic maps, which shows where the model is making changes. These changes make the system usable on every day-to-day laptops and low-powered systems. Since real users use RGB images, we designed a special RGB pipeline. We process luminance separately, apply denoising, and then blend results with the original image. This preserves details with reducing noise. Uh, Now here is the example which was processed by our system. This example shows that our pipeline improves visibility, preserves structure, works across different scenarios. Now these are all examples. Now coming to benchmarking part, we added a benchmarking tool that measures runtime, memory usage, quality metrics, which provides a reproducible and measurable evidence. We also developed a GUI so non-technical users can use the system easily. This allows image selection, parameter tuning, and output preview, all done without a single code or opening the terminal. Here are the advanced extensions which was added by us, such as the video denoising, synthetic data generation, RGB fine-tuning, and model export. This completes the entire pipeline. Here are few results which show significant PSNR improvement, better structural similarity, and clear visual improvement. Noise is reduced while details are preserved. Again, moving on to the results of ELD and comparison against other methods. Here are the quantitative performance summary uh, of the project. Now I'll be moving on to the demonstration of the complete project with benchmarking, GUI, and the deployment. Now I'll be starting with the project demo. Before starting, I'll verify that PyTorch and CUDA are properly configured for GPU acceleration. For that, I'll open the terminal. Here I've already saved all the commands so that it doesn't take much time for me. Going to the project directory, I'll just check. Now, as I can see that CUDA cores are available and PyTorch is also working. This is the actual core part of the project, comprising of multiple parts which I'll be showing step by step. Now, first let me run the project. Now, as we can see, run interference.py is the input of the project, and in test image, we can see the noisy image is present. I'll open the noisy image. This is the noisy image which we'll be using for our testing, and it will get stored in the results demo, which is empty now. So let me run it. Here I am using auto ratio to automatically adjust the exposure, tilted inference which was added by us to reduce GPU memory usage, and save maps to generate diagnostic outputs. This makes the model practical for real-world usage on laptop GPUs. Now we can see the process is being completed and all the results are stored. Now these are various different kind of uh, outputs which was generated. Now this is the actual denoised image which we can see, like the noise was removed. Now I'll run the benchmark. This is the baseline benchmark. This will show the quantitative evidence. It shows runtime, GPU memory, CPU usage. Let's When the baseline is completed, I will run the tiled and we can see the difference. Okay. As we can see, the tiled inference directly reduces GPU memory usage while maintaining similar runtime. This proves that the system is optimized for low resource hardware. This is like almost a reduction by 50%. Now I will show the GUI demo which was done for basic implementation. So this is the GUI which opens up. This is very useful for one who does not want to open the terminal and is not very expert to use the system. Here I am choosing this image which I want to denoise. Now the model is already selected here. I can choose the output where let me choose in desktop results which where it will put the output. In the settings we can auto ratio uh, on or off based on our choice. We can also put strength, tile and overlap. This exposes all major controls like strength, tiling, auto ratio without having the headache of adjusting them in the terminal. So let me run the inference. Here we can see that the denoised image is present, noisy and denoisy image. Now I'll close the GUI and moving on to the another part, that is synthetic data generation, which was again an extension of our project. So this module generates synthetic low light images. It simulates exposure drop, shot noise, read noise, and JPG artifacts. This is useful when real peer data is not available. And finally, again, we also did RGB support, and for that, we provide the option of RGB fine tuning. Now, I will just run for one epoch and show that it's working. It can be run on a very powerful system for better results. Since the PMN was trained on raw data, this lets us adapt it for RGB images. It performs lightweight fine-tuning using synthetic data and runs efficiently on low-end hardwares. Uh, but for better results, uh, better GPU is required. And finally, we provided the option of deployment point uh, or model export. This converts the trained model into torch script format. The F516 FP16 reduces model size, making it suitable for deployment. And the final extension, that is the video denoising. This is very heavy on our system. This extends the model video by adding temporal smoothing to reduce flickering during frames. So that is all I had to show for the live demonstration. Now moving on to the final presentation. After the demo, we have learned that training assumptions matter, RGB requires separate handling, deployment needs optimization, and evidence is important. So final takeaway, this project transformed PMN from a research model into a practical system. It supports both RAW and RGB format. It supports benchmarking. It has the option of GUI and also for deployment in a very low size. So it is both technically strong and practically useful. Thank you for your time.